And we must move along here. That music, to me, is rather motionful music. And the last things we've been studying are things that require motion. Hopefully this computer is now fixed. What we have done is the fundamental point of this lesson, and up till now this is a major point, is the Faraday law for the induction of an EMF. How to produce the EMF by changing magnetic flux through a loop in time, the changing flux. That's the main message. Everything else that we've done is a kind of application of this one law. We had, for example, the generation of electric force, currents, voltage. You've done that in your lab now, so you know what that feels like. And you've done it on a major generator here. Now, what this involves is a rate of change of flux through a loop. So you get some magnetic field times an area, the flux times the loop. And the change of this, change is important. The point I'm going to make today is that the last two things we learned about, capacitors and inductors, are fundamentally depend on time, capacitors and inductors. Because what is a capacitor except an open circuit? And it would be very boring kind of thing if that's all, if you just put a battery on this. Well, what happens? Eventually nothing. It's an open circuit, no current flows. Actually, there's a time-dependent effect that we'll count on. And here also with inductance, it's a spool of wire. That coil is just a spool of wire. And it's a good conductor. So in the long run, it's just a wire with resistance equal to 0. So it's boring. It's boring. It doesn't do anything. But when you have a varying flux through that element, it becomes interesting because then it becomes a generator. It can become a generator. So whereas as a wire, it's pretty boring, it's just a resistanceless, more or less resistanceless thing, just carries current. But that one becomes a generator, and this one you can charge it up, and now it can be a source of charge, and you can use it. It's not just an open circuit, but that depends on time. So that's going to be the motif of this section here. I want to go back and fill in what we left out in chapter whatever it was about capacitors and circuits. Circuit chapter was maybe 24, where there was time dependence involving the capacitor, and there certainly is time dependence involving inductance, because that's essential to the formation of flux. So let's go on to the statement of Faraday's law and Lenz's thing, and we went through all of this, that the trick is you have to get those coils to turn, and when you're generating current through the coils, the very fact that there's current in the coil in a magnetic field means that a force will be acting to resist the turning. So that's the main point here. And we have this alternating current generator, and I wanted to show it, and I will show it a little more detail here, but I wanted to actually give you an equation for the voltage or the EMF that a generator will put out. And again, basically, it goes back to Faraday's law. Except that, you see, in the case of the generator, as we said, what you have is a steady magnetic field. That's constant. There's a flux going through here. What varies the flux is when you turn the angle, and so more or less flux is captured by the coils. So what's important here is the cosine of the angle between the field and the coil. That's what counts. So we can write all that down mathematically. I think this is in the book, so I won't drag it out too much. But the point is that the flux, B dot A, is B times A times the cosine of the angle between them. But the angle is varying in time. With this angular frequency is defined as 2 pi times the regular frequency. So it's the number of angles swept out per second in radians. You may be familiar with that. I won't drag it out. But the point is that it's the number of radians swept out per second. So if you just put in that this is the way the dot product is taken care of. Cosine omega t is really the dot product. The cosine of the angle is varying in time, as you see. The cosine is right now the normal is parallel to the field, so the cosine of 0 is 1, so the full flux is passing through. When I go like this, the normal is this way, it's perpendicular to the field. Clearly, no flux is going through the coil. So that's clear. Good. Okay, so we just put that into Faraday's formula. You take the derivative of that, and with respect to time, the only thing that depends on time is this cosine omega t. So, and cosine becomes sine, and so the amplitude, but the omega comes out in front. That's the key. The omega, whoops. I gotta get out my piece of paper. Where did it go? Yeah. Okay. So the point is omega comes out in front because of that derivative, right? Derivative of cosine is omega t is omega sine of omega t. So that's where the omega comes from, and there's the b and the a. Okay, so the amplitude is proportional to omega, which is the frequency, times the b times the a. And if you have n turns on that coil, each one of the turns gives you an EMF. They all add up in series, and you get omega, I like to write it this way, omega NBA, which stands for, in my mind, Women's National Basketball Association, which goes along with women's lib for the force. So it's a very feminine kind of thing, if you will. So this is the peak voltage put out by a generator. Now, we couldn't show that. Remember, we had this experiment last time where my friends and I were turning the thing, but we were using then a galvanometer, which really couldn't follow the action well. So we put in today, hopefully, an oscilloscope. Now, this can follow the things. So now as I turn it, you'll actually see the waveform that's being generated, I hope. So I'm turning. Can you see that? So there's a peak. It's kind of blip, 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 the voltages. And the rate, the time between is proportional to how fast I'm turning. For example, if I go, now, two things should happen. As I turn faster, the blips should get closer together because I'm generating faster. Also, there's the omega factor in front, which says that the amplitude should change. Because that's, you see, the flux is going to change faster if I get through that loop faster. So let's check that point. That's what I wanted to show by this, that the amplitude will vary with how fast I turn it. So if I go kind of slow, you see the amplitude is about, I don't know what you see, but I see about less than an amplitude, but if I go faster, they get closer together, and I'm generating a higher voltage because of the omega factor. I don't know if I'm off scale there, but see, I'm slowing down. They're spreading apart, and it gets much weaker. So indeed, Faraday's law and the generator law works. You can come and try this yourself, but it's fun watching it. That's the point I wanted to make. So this formula for the EMF, it's varying with frequency, but the amplitude is omega NBA. Frequency, the number of turns, which you would expect, because each turn is adding an EMF. Strength of the field, because that's telling you how much is being cut, and the area gives you the whole flux. So that's pleased that worked out, and I'm glad you saw it. Now we have to move on. Well, here's a power plant driven by steam. It's a little model that sometimes works. And I mentioned to you one of the ways of making a varying flux is by nuclear magnetic resonance. What is happening there is you have a proton which has a magnetic moment, mu nuclear. Very small, because there's just one charge here spinning. And so there's a current in the nucleus of the proton that is spinning, and it has a magnetic moment. And what Felix Bloch did, he put a coil over here and had the moment passing by, and sort of like what I'm doing here. Well, actually, it's different. Here, the moment is moving around like this, and his pickup coil picked up the fact that a flux was alternating through the loop, and this generates an EMF when that moment processes around. Do you remember that little demo I did with the top? You want to see the top again? No. I enjoy spinning tops. I don't know why. Let me do it just for fun. But you got to. It's really not very obvious, actually. No, wrong one. There's a whole book on the mechanics of tops. In fact, there's a famous picture of two great physicists watching a top spin. Niels Bohr and Wolfgang Pauli watching a top. The point is, it's a nuclear moment, and if you put it in a magnetic field, which is simulated here by a gravity field, you get this kind of motion. And if you put a coil here, it's the wobbly motion called precession of the spin. So if I don't want to spin it straight up and down. I want to spin it, whoa, not that bad. I want to spin it. Can you see it wobbling? It's that motion. Bum, 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 bum. Do you see that? When that comes around, if I had a coil here, and that's a magnetic north pole, it'll make a varying field in here, generate an EMF out the coil, and that's the detection of the fact that you've got a precessing nuclear moment here. That could be an electron also. Electrons have magnetic moments, rather larger, and if you can do resonance on them. Get them going, put up a coil here, and you'll pick up the thing. It's this precessional motion. I don't know if you learned that when you did your chemistry NMR. You're just happy to see a spectrum, but that's really what's happening. Okay, well, we can go into that if you want sometime, but there are different ways of varying the flux. But now, the point that I wanted to quickly talk about is this idea of a self-inductance. See here, the varying magnetic field came from outside the coil. But in principle, there's no reason why the magnetic field that's changing couldn't be inside the coil. In other words, suppose I had a spool of wire like this. Now I could have an external magnet, and put flux through here, and I would get an EMF. We do that. That's this experiment. But you can also put current right in the thing itself. And because the current is going around, we know from the right-hand rule, now I haven't made it very clear how that loop is going, but let me try to do it this way then. So if I put current in this way, by the right-hand rule, current going this way will produce a magnetic field inside due to its own current. Now that's a magnetic, that could be, that's its own flux, its self-flux. And if that is changing, that will induce an EMF in its own coil. That's called self-inductance. Which is not quite the same as self-indulgence, but similar. You're doing it to yourself. And the same rules apply. If you try to put current through its own coil, and you try to change the current, or if you change the current, you'll get an EMF coming against you. This is that law. So, for example, suppose I put current in here, and let's say, for example, the current is increasing at this moment. So I have I, and it's going to go to I plus delta I, which means that its flux is going from whatever it is at a certain time to what it was plus more flux, just for example. Okay, so if I have more flux going this way, Lenz's law would say that I'm going to induce a current which will oppose that change. So the flux is increasing this way. I have to produce some flux opposite to it. Right? So the induced current has to be opposite to this because this is causing it to increase. Lenz's law says that I have to induce my induced current is the other way. In order that it's trying to increase that way, the induced current will oppose it. That's right. Now, I don't know if I should do this to you, but I have a revised left-hand rule. Sorry to say. We can make it into a right-hand rule. So you don't have to remember right and left. But you just have to remember that you're dealing with Lenz's law, and Lenz always says that it's opposite to whatever you want to do. So the one way you can do it is use your right hand. If there's a change that way, Lenz would say you want it to be opposite to the change. So you use your right hand, but point your thumb opposite to the change, and that will give you the direction of the current, the induced current, opposite to the change. So the change is this way. Lenz says go opposite. Current will go in the in the direction of your fingers, which is this direction around this particular coil. So we have a right-hand rule number 4, but it's Lenz's law, which says whatever the change is, go the opposite. Your fingers will go in the direction of current. In fact, they'll point to the sense of the EMF. So they'll point to the sense is going to be this way. This is sometimes hard to figure out what is the sense of this EMF, because what this circuit really is like you have a battery or some kind of, but a variable one with an inductance. And what this is saying is that I'm putting current in here, but it's increasing. It's going this way and it's increasing in this particular example, which means that, in fact, the inductance because things are changing, we'll generate a back voltage this way to prevent that increase in flux in the thing. So that's that's the story of why self-inductance occurs. Let me just define. Well, you have to go back to the book, and you'll see that here's the Faraday. Oops, forgot my piece of paper. The Faraday law is just that this is the flux. This is the flux through one turn. If you have n turns of this coil, you will get a total back EMF like that. Oh, I'm so sorry. Yeah, I won't need this anymore now that you've seen it. Oh, I'm so sorry. Thank you. You have the, this is again Faraday's law, and Lenz's, the minus sign. So you have the flux through one turn and the number of turns, and that'll give you the total back EMF. So that's your effective flux. So that's the definition. Okay, that's self-inductance. The next slide says, suppose I have a coil like this called a solenoid, just a tightly wound set of wires. You define inductance as self-inductance as the amount of flux that a current produces by the current it produces that produced it. So it's the ratio of the amount of magnetic flux through the coil to the amount of current you put in. And that will depend on the shape. And for example, we have a simple shape, the classic shape of the solenoid, tightly wound. This is, we worked out a while ago what the magnetic field is in something like this. And I think it was just simply mu zero. Let me stick with the notation of I, with little I. N here is the number. N is the number of turns per unit length. I have to make a small L there because we're going to be using big L for inductance. And so that's the field. The flux is B times that, times A, so that the inductance is going to be N times B, which is times A, and finally, you'll have N, B, A. Okay, but B is mu zero N I times A over I. And the I's cancel, so that the inductance will be N mu zero. Well, this is another N, which that's the number per unit length. So we can just put in N over L. So 1 for N times A. So you have two N's here. You have N squared, big N, mu zero, A over L. So that would be this would be the inductance of a solenoid. Let me put it down here because we want to make some comparison to other things that we know. The inductance is mu 0 n squared A over L. The comparison that I'm going to remind you of is that the capacitance is epsilon times epsilon naught A over L. And the resistance, R, is rho L over A. So, again, the pattern is there is a geometrical factor, the length, the area. There's a materials factor. And here, there's a geometrical factor, A over L, the capacitor, and there's a materials factor. This is an empty space, epsilon naught. This is if you put something in the capacitor, like a water or ferroelectric or something, you will get this dielectric constant, or sometimes we call it K, kappa, the dielectric constant. So it's sort of the material that you stuck into an airspace. Similar thing is going to be true here. If you have an inductor, self-inductance, in air, you put mu 0. If you should put, as in this case, you see, this is a very large inductance, but to make it even stronger, they put in a chunk of iron in here. It turns out that what you do when you put the current in, you get a magnetic field due to the wires, but you also magnetize this chunk of iron, you get even a bigger field. So then you would account for that by having it's called a relative permeability. And so there's your materials factor. And here's your geometrical factor, the number of turns, the area, and the length. So these things, and you'll notice that they don't depend on at least in the simplest case, they don't depend on the field that you're putting in, the current. They are just the material and a geometrical factor. In fact, in truth, in real life, rho, the resistivity, can depend on temperature. In some materials, it actually depends on the current that you put through. But in the simplest case, which for now we're dealing with, this is a constant. This material constant is a constant also. And so that's the analogies we have there. Point that out for starters. Now, one of the tricky things is to figure out what sense this generated EMF is. See, as I said before, the inductance is just a wire. If the current is not changing, it won't have any voltage drop across it. It's just a resistanceless wire, ideally. But when the current is changing, there's a flux change, and it becomes a battery. That's a very important idea. And to get the sense of that change, you can go through the Lenz's law argument, or, as you might fear, I've come up with yet another rule that you may not find in books, but here it is. That is, we just examine all the cases. You could have, for example, the current going to your left and changing current in the same direction. Now, the EMF that will be generated will be opposite to that because it's trying to fight the change. So you see the EMF on that inductor is plus to the right because it's opposing, it's trying to prevent that, trying to send current the other way against the change. Get that? Now, for example, suppose I put the current going to your right. But now there's a change in current is going to your left. So now the current is decreasing because it was going to the right. I'm putting in a current going to the left, so the current is actually decreasing. So that's the change in current. And you see that the EMF opposes that change. That's the important. It doesn't matter what direction the current is going. The important thing is which way the change is going. And the EMF that you generate will be opposite to the change. It will try to prevent the change. So that's the point of this. What you want to look for is a simple rule. The EMF is just opposite to the direction of change. That's the result. These are the 4 possible cases. And all you have to remember is you want to oppose change. Nothing political in that, but that's just the way it is. So here is my newly revised right-hand rule number 4. You put your thumb in the opposite direction of the change, and your fingers will turn in the direction of the induced current, and your thumb will point to the positive pole of the positive EMF. You can work on that. But let me now talk about changes with time of these elements. Now, again, I like to be somewhat systematic in my organization of the things so that I can think about them more clearly. I don't know if this works for you, but in any case, let me try. Here's a resistor. Now, suppose first I say, what is it? Fundamentally, what is it? Let me put the lines in a different place. What is it? And let's say a resistor. Well, fundamentally, it's sort of a clogged pipe full of water, full of charge, say. Now, what is a capacitor fundamentally? It's an open circuit. It's a gap with a couple of plates attached. And what is an inductor? It's a wire rolled in a spool. So it's basically a wire with R equals 0. And this is basically an open space with infinite resistance, fundamentally. So if there is no time variation, that's exactly what they'll do. No current will pass through this, and this will pass current freely. And in fact, you would say that I must be 0 because the resistance is infinite. And in this case, because the resistance is 0, the voltage must be 0 for steady or steady current, steady voltage. Right? Now, again, there's nothing new here. I'm just applying the ideas we already have. So in case you don't remember it, just go back to basics and figure it out. Again, just think, what is this thing? And you can figure it out. There's nothing, no new ideas. Now, let's see what happens, though. Suppose the voltage is not steady. V varies. Now, I'm going to imagine something like this. I'm going to have the voltage of a circuit. Let me make a circuit here, for example, a battery with a switch and a resistor. Let me put a resistor here too, R1, R2, and then I'm going to attach these various elements across here. And I'm going to see what happens if I should open and close this switch. So I'm going to, after a certain time, I'm going to open it, put the battery voltage on the circuit, and then at a certain point, I'm going to turn it off. I say at time 0, I turn it on. at time big T, I turn it off. So let's see what happens if I should put a resistor over here. Here's my test resistor. Okay. And I'm going to do a similar thing with a capacitor. Put a resistor here, and a capacitor over here. Or I'm going to do the same thing with an inductor. And let's see how they behave when I turn that voltage on and off. I can get rid of this, can I? Okay, so now here is my voltage as a function of time. In other words, I've closed the circuit on this resistor circuit. And I want to know what is the action here. Well, what's going to happen is that the current will, at t equals 0, jump up. It will follow the voltage. The current you can figure out is this is R1 and R2. Well, that's a little circuit problem where you figure out, so this current, this is an equivalent resistance, and there's a certain current flowing through this branch. It will split here. Part of it will go through R, but it will go through immediately. And when the current, when I open the circuit again, the current will drop down at big T time, and the voltage on that resistor, this one here, this is the current through that resistor. It will follow quite in step with this, and you can figure out what the voltage here would be, because this voltage of the battery is partitioned between this one in series and this combination. But you could figure that out, and things will follow. The important thing is the time dependence that I'm interested in right now. You can do this circuit, and you should. But the capacitor, on the other hand, is a different world. If you close the circuit on that, you have to remember that, again, going back to basics, the capacitance is equal to the charge over the voltage. And so the voltage is equal to Q over C. Now, when you first close the circuit, there is no charge on the capacitor. So the voltage on the capacitor, at T equals 0, the voltage on the capacitor must be 0, because there's no charge on it yet. Interesting. But as the current flows, charge will go onto the capacitor, so it rises up. And eventually it reaches some level appropriate to the voltage on it. And the current, let's see, we have to have a current too. Now that's interesting. The current actually, at T equals 0, the current, because there is a quick surge here, the current actually spikes up like this and drops down. Eventually this voltage that you're applying is steady. So once there is a steady voltage on here, there's just a steady charge on here, so the current stops because this is an open circuit. So here, oddly enough, we call this X. We don't want to call it R. X is the it's the equivalent of resistance for these time-dependent circuit elements. It's called a reactance. So basically, if you think of it as a resistance, it's actually zero here, and it goes to infinity here, because you see here again, this argument would be the fact that there's zero voltage on this means that if you were thinking of this as a resistor, it would be a short circuit. It has no voltage. IR would be zero. So, but the fact that the voltage is zero suggests that IR being zero, you could think of this as being a short circuit. So this acts like a short circuit over here. It sounds like a wire over here, and over here it acts like an open circuit, which it is, because here the voltage is settled down up to this point. So you have an open circuit over here. It's a little bit crazy. Am I leaving you behind? Yeah? This is the current. Well, what happens is that first, when you turn on the voltage, the current, there's nothing over here to prevent it from flowing. So the current quickly rushes over, starts adding charge to this capacitor. It builds up. See, the current is coming, it builds up, and it starts resisting the oncoming flow. Yeah, this is getting plus, this was plus, so eventually it's going to charge up to a voltage such that it will cancel the voltage coming from the battery. So this current will stop. In other words, again, going back to the argument that over long times, it's an infinite resistance, so the current must be zero over long times. So this would argue that if you put current through a capacitor, you can get current at the beginning, but if you wait long enough, it's got to go to zero because it's an open circuit. If you have a steady voltage, eventually it's going to go to zero. So eventually it's going to show its true nature, which is it's an open circuit. And you put on a battery, it will eventually stop flowing. Pardon me? Say again, please. What would be flat? The current would be flat when?
For the third case.
For the third case, inductance, we'll get to that right now. Yeah, I have about 5 minutes to knock this off. But no, it turns out that these are kind of opposites to each other. So for the inductance case, if you were to make a circuit like this, what's going to happen, and here's your inductance. When you close the switch, you have a sudden attempt to push current through that inductor. And the inductor, if there's a fast changing current, it will create a back voltage. So it will create its own voltage, which will stop the current. So if I were to plot the current in the inductor, it's just the opposite. The current is zero to start. It doesn't go up at t equals zero. It's zero. So at t equals zero, it's acting like its x is like infinite. It's an open circuit. In fact, in the radio world, inductors are called chokes. I don't know, did anybody ever hear that word? A choke? Because if you try to push things through it, it chokes. It doesn't go. If you go too fast, it chokes. So it chokes. At this point, it chokes. So you get nothing. But as the current doesn't go so fast, gently, then the current goes up. Because eventually this thing's going to act like a wire, and so it's going to let the current through. But at the beginning, it's acting like a battery in reverse polarity. So that's why the current goes up and it stabilizes, because now the impedance here is zero, because it's a wire. Yes, sir?
Sorry, why is it reverse polarity?
Well, because you see, you're trying to push the current through this choke, and it builds up a reverse polarity to the one that's trying to make it go. This is the polarity of the EMF that is induced in that self-inductance. You see, you're trying to push current through this way. It says, no, I'm going to build a battery the opposite way. So you're trying to push current thing? No, I'm going to make a battery to push current the other way. Yes, sir?
That's Lenz's law in action.
That's Lenz's law in action. Full blast. Lenz's law in action. That's the minus sign in that Lenz's law. It says if you try to push current through this inductor this way, it's going to develop a battery voltage to push current the other way. It's just obstinate. That's the way they work. And so at first, if you try to push too hard, it chokes it off entirely. You get zero current. And in fact, you can then, by the same argument, the voltage on that L at that point jumps up. Well, it jumps down, actually, because it's sort of opposing. It's the opposing voltage. So the voltage actually goes negative in the sense that it's opposing the battery voltage. And eventually, that voltage is due to d phi dt. You're trying to push flux through there? No way. It's going to build up a voltage to fight that. And then when if the voltage drops back down, what happens is this thing dies off, and you get a kick the other way. Because again, by turning it off, you got a sudden change. It doesn't like that either. So it's actually going to switch its battery voltage. When you turn it off, the inductor at this point will be, because current was going through. See, current was going through this way after a while. See, after a while, this thing the current is going this way. But when you try to turn it off, it's as though you're adding a delta I in the other direction. And this thing says, no way. I don't want delta I. I'm going to do my right-hand rule. I want to maintain the current. So I'm going to generate a voltage this way to try to push current, to continue the current and fight the change. It's tough, a little tough going, this. But think about it, it makes sense. So over here, you're going to get a voltage change, and the current will go from what it was as a wire down to the fact that there's no voltage on this anymore. So, well, I tell you, for your exam, let me say, this part is capacitors are on the exam, and this general idea is in that chapter. I hope this helps a little bit. I don't know if it does, because it's. But you want to just know the nature of a capacitor is such that only when it has charge on it does it have a voltage. And at a long time, it's an open circuit, so it carries no current. It could have charge on it, but the charge can't change if the current is steady. So this is really, if you think about it, go home and think about it. You see, it really isn't too strange. This one is a little harder because of the Lenz's law thing. But if you can, all right, for time being, worry about this for the exam, okay? And I'd appreciate what a capacitor is and how it acts when you try to do it, move it. So what it is when the current is changing fast, it lets current flow through. When the current is changing slowly, when it's DC, it's an open circuit. It switches its nature from a short circuit to an open circuit. And this one switches its nature from an open circuit to a short. So they're just kind of opposite. I could maybe make a little table here if you're willing to wait a second more. At t equals 0, the capacitor is a short. This is when it's turning on or fast changes. Let's say fast changes. And here at a steady voltage, steady applied voltage. The capacitor, for fast changes, it acts like a short, like a wire. And for steady changes, it's open, because it is open. It's an open circuit. But the inductance, for fast changes, it's a choke. It's like an open circuit.